Hi everyone, in this video we're going to look at change of variable in multiple integrals. We've already done three special examples of this, which are polar, cylindrical, and spherical. This one is going to be much more general. So an equivalent of this in one dimension would be something called the U substitution that you recall, where if I have an integral of f of x dx, and maybe it is not directly solvable in this form, what we do is we set x is some function of u. So this is a form of change of variable. And we find that when we do this, this integral becomes integral of f of g of u, and the dx part becomes g prime u du. So whenever there's a change of variable, even in single integral, there are some things that fundamentally change. For example, x gets replaced by g of u, which is the substitution. And as you can sort of connect it to something you've seen before, the same thing happens in polar coordinates, right? So when you change to polar coordinates, we go f of r cosine theta, r sine theta, and then we have an r dr d theta for multiple integral. And the dx, the integrating element, changes to g prime u du. And for one dimension, this is a standard procedure which works for any kind of change of variable, meaning u could be any function, or x could be any function of u. And our goal is to have something similar, a result that is similar, but in multiple integrals. So for example, if I was working with this particular problem here, then I would set x equals root u, or u equals x squared, right? And my g prime u is then 2x dx du. So this entire integral becomes sine of u, which is f of g of u, times g prime du, which is 2x, and this whole thing just becomes du. And this is negative cosine u plus c, which is negative cosine x squared plus c. So that was in single integral. In double integral, the first example that we looked at was polar, where x equals r cosine theta and y equals r sine theta, so that x is now a function of r and theta, and y is another function of r and theta. And what happens in this case is the region R becomes the region, we just use a different variable S to keep in mind that we are dividing it in a different way now. And we get R cosine theta, R sine theta, which is very similar to f of g of u here. And the integrating element, the dA, becomes R dr d theta. So that is, there is a transformation. Now let's move on to something that's a little bit more general, which is called a general transformation of space. So anytime we do a U substitution, a change of system into polar, what we are actually doing is we are transforming the space into a new space. So what is a transformation? T is a function, the transformation, T for transformation, that maps one space into another. Such a function is called a transformation. So a simple drawing-based example would be, suppose I have a space denoted by S, and when we use the word space in math, it just means a set of points, could be in any dimension. So we have this set of point S, and suppose I have this point here, which is given by u1, v1. Then what a transformation does is it takes this point and maps it to possibly another space that doesn't have the same shape, dimension, same number of points as the original region, but it will satisfy certain conditions. For example, you will be able to find mappings for every point to every point. And suppose here is x1, y1, then an example of a transformation will map this point to u1, v1, and vice versa. So this would be a forward transformation, and this would be the inverse of the transformation. Meaning you can take any point on S and there will be a corresponding point on R, and you can take any point on R and there will be a corresponding point on S. So the transformation may or may not be 1, 1. For example, if there are squares and square roots involved, you will not have, one may map to more than 1 point. If it is, then that's a nice transformation, which is called a 1, 1 transformation. So a transformation is basically just a function, right? So what you have is you take a transformation of x and y becomes some function of u and v. So you can think of transformation as a function. It's a function whose domain is some set of points on the space, right? So again, it's not that they are the same thing, not that functions and transformations are the same, but transformations can be seen as or written or expressed as functions. Let's look at an example where we don't do any calculus. We're simply looking at how space gets transformed and how that affects certain shapes. So for example, a transformation is defined by x equals u squared minus v squared and y equals 2uv. And we are asked to find the image of this square under this transformation. So before we get to the square, let's look at some other stuff, right? So for example, let's see. So going from the uv world into the xy world, we can look at an example. For example, if u equals 0 and v equals 0, so that would be the origin in the uv world, then we get x is 0 and we get y is 0, which means the point 0, 0 maps to the point 0, 0, which is good. What about, let's say, a point 1 and a point 1? Then x is going to be 0 and y becomes 2. So which means the point 1, 1 maps to the point 0, 2. Now if I take u is 1 and v is 0, then I get x is 1 and I get y is 0. So the point 1, 0 maps to the same point 1, 0. And if u is 0 and v is 1, then I get x is negative 1 and y is 0. So 0, negative 1 maps to negative 1, 0, and so on. So you get the idea here. That is, every time we plug in different values of u and v, it's going to give me some point in the xy world. Now, in this particular problem, it's not asking me to find all the points, which is not possible because there are infinitely many, but it's asking me to find the image of a square in the uv world. So in the uv world, I have a square. The square is defined by u between 0 and 1 and v between 0 and 1. So let's call this the u-axis and the v-axis. So what we have is this square with the corners at 0, 0, 1, 1, 1, 0, 0, 1. And we are trying to find, this is the region S, and we are trying to find how it maps into the region R in a regular xy coordinate system. So what we do in this case is we are going to break this down into sides. So we will look at this side, call it S1, then we will look at this side S2, then we will look at this side S3, and lastly we will look at this side S4. So when I am on S1, what is true? I am on the u-axis. So on the u-axis, v is 0 and u lies between 0 and 1. So x, which is u squared minus v squared, is simply u squared, and y is 2 times u times v is 0. So x, we have x equals u squared and we have y equals 0. So how does that map into our R world or the xy world here? Let's look at that. So S1 will correspond to y being 0. So which means it's on the x-axis. And how does it vary? X is u squared, so it will also lie between 0 and 1. So this is going to be the image of S1 here in the transformation. So that's what S1 is mapping to here. Okay, let's look at S2. S2 is u equals 1, and then v is going from 0 to 1. So x becomes 1 minus v squared, and y becomes 2v, where we can eliminate v to get x equals 1 minus y squared over 4. And this we know is a parabola. So it's a part of a parabola. So what does this map to? This maps to x equals 1 minus y squared over 4. So that's what S2 is mapping to. Similarly, let's look at S3 now. For S3, we have v equals 1, and then u changes from 0 to 1. So we have x is u squared minus 1, and y is 2u. Now, same thing here. In this case, we will eliminate u to get x is y squared over 4 minus 1. But in this case, the coefficient of y squared is not negative, so we will have this as the third part. So x is y squared over 4 minus 1. So x is negative and goes to this point negative 1, 0. And lastly, for S4, the side S4, we are back to having, or we are at u0 and v is 1. So we get x is negative v squared and y is 0. So we're back on the x-axis, and in this case, we will be over here. So that means that this particular square in the problem got mapped to this shape, which consists of the x-axis, a part of the x-axis, segment of the x-axis, and two arcs of parabolas that meet at the point 0, 1. And as you can see, all of these four mappings also work out. Sorry, this is going to be 0, 2. Right, so all of these four mappings can also be found here. The origin, end of S1 is 1, 0. End of S2 is 1, 1, which is 0, 2. End of S3 is 0, 1, which is negative 1, 0. And then back to the origin. So that's how you can find images of these specific regions. So this is just about how spaces get mapped from one world to the other depending on the functional relationship between them. So the next question is, what is the effect on the double integral of having doing this, right? So what happens when you apply these generic changes in the double integral is that instead of having a nice flat rectangular region, you will have a region that is probably or possibly curved, a little bit curved. So everything is a little bit curved. And what we are going to do is we're going to use the power of approximation and the infinitely small particles that we have, which kind of cancels out everything. And we are going to estimate the area. We're going to say that the areas are going to be almost the same. are almost the same. And so we know that if you have a vector A and a vector B, then the area of the parallelogram is given by the absolute value of the cross product of this. This is something from Calc 1. And something pretty similar happens here, which is these functions or these vectors become the tangent vectors. So these are tangent vectors in the u and tangent vectors in the v direction. And so our adjusting factor is going to be the cross product between these tangent vectors ru and r sub u. R sub u and r sub v. And this is called the Jacobian. So the Jacobian of the transformation t given by x equals g and y equals h function is, this is the notation for Jacobian, partial xy over partial uv. And what it is del x del u, del x del v, del y del u, and del y del v. So it is the determinant of this particular matrix. And this is obtained by taking the cross product of this. So you can consider this as an extra credit problem. So recall what each of these vectors are, right? So ru is del x over del u is this vector, del y over del u, and rv is the vector del y over del u, del x over del v, del x over del v and del y over del v. So if you actually find this, it should come out to give you this determinant. And that's what the Jacobian of the transformation is. So the result says that suppose T is a C1 transformation whose Jacobian is non-zero, and T maps a region S in the UV plane into a region R on the XY plane. F is continuous on R, and that R and S are type 1 or type 2 plane regions. Suppose T is 1, 1 except perhaps on the boundary of S. So it's possible that it is not entirely, it has to be 1, 1 on the interior, but on the boundary there can be overlap. Then taking this double integral is the same as taking the double integral of this, where the adjusting factor is your Jacobian. The Jacobian of the transformation is your adjusting factor. And we can quickly verify this for polar, and then we will end this video and do the examples in a next video. So what was the relation in polar coordinate? In polar coordinate, we had x is r cosine theta and y is r sine theta. So what is the Jacobian here? We expect the Jacobian to be r, because that is the adjusting factor we place, right? So we have del x over del theta is going to be negative r sine theta. Then we have del x over del r, which is cosine theta. Then we have del y over del theta, which is r cosine theta, and del y over del r, which will be sine theta. The determinant is the cross product, so we have negative, so absolute value of negative r sine squared theta minus r cosine squared theta, where this gives you r because sine squared plus cosine squared is 1, and that is our factor. And once again, there will be, I'll give you one extra credit problem here. Actually, I'll give that later because it involves 3 variables, so I do have to show you what the Jacobian looks like when you have x, y, and z. It looks very similar, like, nothing much different, but okay, so I'll do that in a future video. That's it for this video. This became a slightly longer video than expected. We will look at some more examples in the following video. Thanks, everyone.